There we go. Now we're recording. Good. So, good. So where are we? So the exam problems are also posted. So the exam examples are already posted on Blackboard, as well as the extra credits for the 5th exam is also posted on Blackboard. So all that is all up there. So whenever we can get to those things, you can actually start working on all that. And yeah, so basically we just have the 4 days left. So things to talk about for the 5th exam. So hopefully I'll have the 4th exam graded here in the next couple days. So hopefully we'll be able to see what your average is by then. So when it comes to the 5th exam, so the 5th exam will be the last exam, but if you are happy with your grade going into the 5th exam, then you don't have to take the 5th exam. Okay, because we do drop the lowest exam. So that means if you've done well on the first 4 exams, then you don't have to take the 5th exam because you can just use that as your dropped exam. Unless you have something else that you already is a much lower grade, then you want to replace that one, then you obviously won't want to take the 5th exam. Other things is, remember, I do keep all the extra credit from all the exams. So if you decide that you're not going to take the 5th exam, at least do all the extra credits. So at least the extra credit will still count towards your final grade at the end of the semester. So again, if you are happy with your grade, if all of your grades on all of your exams have been good going into the 5th exam, so again, you don't have to take the 5th exam. You can use that as your dropped exam, and it won't hurt you in any way to do that. But again, make sure you do all the extra credit because you can still use that towards your final grade. Okay. So again, hopefully I'll have the 4th exam graded here in a couple days, so that way you can see and then make a judgment by then on whether you want to take the 5th exam or not. Or you can always decide you want to take the 5th exam, and then, you know, it's totally up to you. So good. So anybody who is taking MCATs and things like that are going to do pre-meds and things in the future, you will obviously want to pay attention to all the material because all that will be part of the MCATs. But anyways, that's all I want to say about the 5th exam. So again, if you're kind of happy going into the 5th exam on your grade, then again, you don't have to actually take the 5th exam. You can just use that as your dropped exam. But again, if you have a low grade for one of the other exams that you want to replace, then by all means take that 5th exam. So good. So basically, we're going to start chapter 22 today. So 22 is about Maxwell's equations and electromagnetic radiation or light. So let's talk about this. So basically, what did we know? So going into around the late 1800s, so we're talking around 1890s-ish, what we knew is we had something which was what everybody called light. We didn't know what light was. So basically what we knew is we had electric fields, so we had electricity. We knew we had magnetic fields, so we knew we had magnetism. But we had this extra thing, this extra field, which was light. So what everybody kind of thought at that time was that these two things were separate. So that there was the theory for electricity, there was a theory for magnetism, but nobody understood that these two things actually talk to each other. And we didn't know that light was actually part of these two things. We just thought it was some extra field because what we knew was that it wasn't some sort of charged particle. So we knew this wasn't a charged particle. So this was not a charged particle. And we knew that because if we brought a magnet near the beam, so near light, it wouldn't deflect in any way. So we knew it couldn't be a charged particle. So not a charged particle. So we didn't actually exactly know what it was. And what they also knew was that the speed at which it traveled was roughly about 3 × 10⁸ meters per second. And the reason that they actually did that is they actually took mountains. So they took one mountain here and another mountain here where they knew the distance between the 2 mountains. So here was some distance. And they put one guy on top of this mountain and another guy on top of this mountain. And they agreed at some time that this guy was going to shine a light. So basically he had some light here and then he would shine the light at a given time. And then he would measure, knowing the distance, the amount of time that it took for it to go from this location to this location. So then knowing that, what they found was that the speed of light, which is what we call c, was about 3 × 10⁸ meters per second. Okay? So as I said, so about 1890s-ish, we knew we had light. We knew it wasn't some sort of charged particle, and it was just some other field. So this was some other field. We knew we had electricity, we knew we had magnetism, but we thought these two things were separate, so we had a completely different theory for electricity and a completely different theory for magnetism. Except one thing that kind of stood out in magnetism was actually Faraday's law. So the thing that we finished off for last exam. So again, what Faraday's law says is that what? If we have a time-changing magnetic flux, or more appropriately, a time-changing magnetic field, this would then induce an EMF. But remember that an EMF is the same thing as the integral of the electric field times the differential length times cosine of the angle between the two, okay? Because the EMF is nothing more than a change of potential. So basically what Faraday's law basically said was that we can actually induce an electric field, let me put my negative sign here, by having a time-changing magnetic field. So basically what that implied then was that a magnetic field, or sorry, an electric field, can be induced by two things. So this told me that an electric field can be induced by simply charge and a time-changing magnetic field. Now, going back to then magnetism, we know is that magnetism at this time, B, can be induced by moving charges, i.e. currents. So there's almost a symmetry between these things. So electric fields can be induced by charge, magnetic fields can be induced by moving charges, but an electric field can be induced by a time-changing magnetic field, but there's no such portion for the magnetic field. So what Maxwell, James Clerk Maxwell said was that, well, let's look at these things a little more in depth. So what Maxwell said is, well, what would happen if we can induce actually a magnetic field from a time-changing electric field? Okay. And if that was true, then there would be an absolute symmetry between these two fields. Right? So in that case, then the magnetic field will be induced by moving charges, an electric field will be induced by stationary charges, the electric field would be induced by a time-changing magnetic field, simultaneously the magnetic field would be induced by a time-changing electric field. So Maxwell basically proposed this, was that we can actually induce then this magnetic field by allowing an electric field to actually change. And this wasn't actually strange because if we really think about, say, a parallel plate capacitor, so let's say here's my parallel plate capacitor. So let me put my parallel plate capacitor here. So here's one plate. Here is my second plate. And then I have current. So what happens? So I have current running here. I have current running out on this side because we know we're going to have charges lining up on here. So I'm going to create charges on here. I'm going to create negative charges then onto this one, and then I'm going to have current running in this wire and then this portion of the wire. Well, what's kind of unique about the parallel plate capacitor is if I took a simple circuit and I connected it, say, to a resistor, and then I'm running current through it, so I have current running through this, but what happens if I cut the wire? So let's say I come in and I take some scissors, so here's my scissors. My beautifully drawn scissors, there we go. And I snip this wire and I cut it. What would happen to the circuit? So if I had my EMF here, I'm running a current through the wire and I have a simple resistor, and I go in and I cut one of these wires, what would happen to my circuit? Could I have any current running through my circuit? No, that's right, Keenan. No. So if I simply came in with my scissors and I cut the wire, I would break my circuit and this thing would no longer be allowed to flow. I would no longer have current running in. But if I go back to my parallel plate capacitors, right, we're going to have a wire here, I have one plate here, I have another plate here, and I have a wire here. So I have current going here and I have current coming out through here. But the question is, what happens in between these parallel plate capacitors? Because that's effectively the same thing as cutting the wire. I have no no charges actually passing from this plate to this plate. They're not jumping from this one to this one. This one is building up positive charges. This one is building up negative charges. So I have nothing in here which is actually continuing the current going through, which means that I actually is the same thing as kind of cutting the wire. But the difference is here I actually have no current running through my system once I cut it. And this one I do have current running through. So what's the difference? Well, the difference is since this plate here is accumulating charge over time, this plate is also accumulating charge over time. Then what's happening inside of here is I'm actually inducing an electric field, which is changing with time. So what happens then is when I connect this guy to simply a battery and we measure the current which is running through the battery or measure the current running through the circuit, what ends up happening is inside of the parallel plate capacitor, we have something that acts like a current but isn't actually a current, which is what we call the displacement current. So the displacement current, the thing that actually acts like a current, which carries the information that current should be flowing through here, is actually proportional to the change in the electric field with respect to time. So it turns out Maxwell's proposal is actually correct because we see it all the time with parallel plate capacitors, we just never actually really thought about it. So what's really happening is inside of the parallel plate capacitors, why I have currents running through my system is because inside I have a time-dependent electric field. That time-dependent electric field acts like a current, which then induces a magnetic field. So inside of here, I still have a magnetic field, just like I would around the wire, or that magnetic field would be running in this direction. So in here, I would still end up with a magnetic field running in the same direction. But again, the difference is this one is induced by moving charges, where this current here is induced by the time-dependent electric field. So when this thing reaches maximum charge, this side also reaches maximum charge. The electric field then becomes a maximum, which means there is no more changing electric field, which means the current then would go to 0. Same thing as the current here, because I have no more charges running through. So what Maxwell did is he basically proposed this portion added to then Ampere's law, which is a law that we never talked about, but the way that we actually would induce a magnetic field, which then completed that symmetry. So now the electric field is created by stationary charges and the time-dependent magnetic field, where magnetic fields then are induced by moving charges and then time-dependent electric fields. So these two things have complete symmetry to them now. So what Maxwell also did is he then used this to then rewrite all of electricity and magnetism into 4 beautiful equations, which are known as Maxwell's equations. Let's talk about Maxwell's equations. So the first Maxwell equation is what's known as Gauss's law, which is basically a generalization of Coulomb's law. Number 2 is what's known as Gauss's law for magnetism, Number 3 is what's known as Ampere's law. We'll talk about each one of these kind of in turn. And then the 4th one is Faraday's law. So basically what Gauss's law says is that electric fields are created by charge. So generated by charge. Gauss's law for magnetism says that there are no magnetic monopoles. Faraday's law, I'm going to skip number 3 here for a second. Faraday's law says that electric fields are generated by time-dependent magnetic fields. And then finally, Ampere's law says that magnetic fields are generated by current and time-dependent electric fields. So these are what we call Maxwell's equations. I'm not going to write down their actual structures because they involve a lot of higher level mathematics that you guys don't ever technically need to know, so we're going to skip that portion. But basically, what Maxwell went on further to do was then take these two, Ampere's law and Faraday's law, and then predict light. So what Maxwell actually ended up showing was that Faraday's law and Ampere's law working together actually end up predicting light. So what Maxwell ended up showing was that light was actually an electromagnetic wave. So he showed that this was an electromagnetic wave. And what he went on to show was actually the speed at which that wave travels in vacuum is equal to 1 over the square root of epsilon naught times mu naught. So this is the permittivity of free space times the permeability of free space, which is then roughly equal to about 3 times 10 to the 8th meters per second. So this was all Maxwell's basically contribution to electricity and magnetism. So he proposed this extra term, where this extra term was this guy. He added this on to Ampere's law, which means that this is actually known as Ampere's Maxwell's law. Let me notice that one. There we go. Or Maxwell's Ampere's. And then this term, along with this term from Faraday's law, together then predict light. Okay. So what he ended up showing was that indeed, electricity and magnetism, basically just using these two, gave you an electromagnetic wave, where that wave then moves in vacuum at approximately the same exact speed at which they were measuring light to go. Where the speed of light, which is 1 over the square root of epsilon naught times mu naught, is about 3 times 10 to the 8th meters per second. Now, what's the most unique about this was the first time in physics history where somebody predicted something before they experimentally measured it. So what had always happened in physics was that somebody had measured something experimentally, and then they ended up doing a whole bunch of different experiments based off of that, and then built a model from there to explain that physical phenomenon. But this was the first time in physics history where somebody actually first predicted something using theory, and then, in fact, after they did that, they measured it experimentally. So the theory actually came first in this case instead of the experiments coming first and then the theory coming after that. So this was all what Maxwell did. So Maxwell added this portion here, and then this portion along with this portion, use my highlighter here, are then the key portions of light. So without this extra piece, light could not actually be possible with inside of electromagnetism. So, and to make it a little more concrete, remember that this one actually has a negative sign out front. So let me go ahead and put my negative sign, where this one actually has a positive sign. So here, what this one says is that as the electric field changes with time, that promotes the magnetic field to grow as well. But as the magnetic field grows, that then has the negative sign, which then causes the electric field to then start to reduce. So these two are actually simultaneously feeding off of each other, where this one, as he gets bigger, but as he gets bigger, this one then starts to get smaller. So this is that restoring force that you need when it comes to a wave for the harmonic oscillations. Right? So these two things together gave us light. So this is light. Right? So remember that light, what we talked about way back when, is actually an electric and magnetic wave, which are then simultaneously oscillating, where they're oscillating 90 degrees away from each other. So basically what's happening here is that, say, for example, the electric field is oscillating along the X direction, the magnetic field then is oscillating along the Y direction, while the entire wave itself is moving in the Z direction. Okay. So these guys are 90 degrees away from each other. They're actually in phase with each other, which means that they have exactly the same phase factor. But again, what's happening is as the electric field grows, so that's this one, the blue one. So as the electric field grows, that's causing the magnetic field to also grow. But as the magnetic field is growing, that then causes the electric field to decrease. So this is actually what's giving us that restoring force to give us a wave. So good. So these are Maxwell's equations. So again, without this extra term that Maxwell actually promoted and actually proposed, we would never be able to generate light. So again, the big deal about this is that this was the first time that theory actually came before experiment, and that he actually theoretically predicted it, and then the experiment showed that he was actually correct. So good. So the next question is, well, how do we actually generate light? So how do we generate light? So generation of electromagnetic waves. Okay. So typically, to generate this, we need to have some sort of time-dependent field. So time-dependent field. And the way that this is going to work is that we need to somehow accelerate charges. So to create the light, we need to accelerate charges. So one way we can do this is actually using an antenna. So let's talk about an antenna. So how does an antenna work? So an antenna, we're going to take two rods. So there's going to be one rod here and say another rod here. And then we're going to connect these guys to some AC generator. Okay. So this is our typical sign for AC. So this means we have some sort of AC generator. So what happens? So let's say initially there is no current at t is equal to 0. And then what we're going to do is we're going to start to have current flowing in this direction. So we're going to have current flowing like this. So what'll happen is that this side will start to gain positive charges. This side then will gain negative charges as the current is flowing through. Right. So basically what will happen is at t is equal to 0, we have 0 currents running through it. So we have 0 charge as well. But then as time goes on, we're going to create more and more and more charge by having more charge placed onto here, which means that we're going to create an electric field where that electric field then will point from the positive to the negative. So I'm going to get some sort of electric field. Draw a little bit nicer here. There you go. So I'm going to get an electric field that does something like this. So I'm going to get an electric field that's going to do that. Okay. Simultaneously, we're going to create a magnetic field. That magnetic field is what? Now we have current running in this direction. So I'm going to put my thumb in the direction of the current, curl my fingers around in the direction of the magnetic field, which means my magnetic field is going to do something like this. In the direction of my magnetic field. Okay. So here I have magnetic field lines going in. And then here I have magnetic field lines going out. So what happened is the current is going to keep going, and then eventually it's going to reach then maximum amount of charge, but then the current is going to start to switch and go the opposite direction. So the current will still be pointing upward, but then the charge is going to start to decrease, which means the size of the electric field is going to get smaller, the size of the magnetic field is going to get smaller, until eventually everything's going to switch. Right? Until eventually what's going to happen then is this side is going to become negatively charged. This side is going to become positively charged. So that the electric field then is going to point in the opposite direction. So now what's going to happen is my electric field is going to point this way. Simultaneously, my magnetic field will also switch direction. So that's going to rotate in the opposite direction. So here I'm going to get magnetic fields going this direction, this direction, this direction, this direction, this way, and this way. So now over here, the magnetic field lines are coming out. And on the other side, they're actually going in. Okay? So basically what happens is in the antenna, I'm going to have alternating currents going in opposite directions. So one direction is going to go up. It's going to go from 0 up to a maximum and then decrease back down to 0 and then switch direction, which means that the electric and magnetic fields will then constantly switch directions. So if I plotted, say, the electric field versus time, so let's put time on this axis, electric field magnitude on this axis. So again, if time is equal to 0, we have 0 electric field. Time increases, the size of the electric field will start to get bigger until it reaches some sort of maximum. And then it's going to start to decrease until it reaches 0. And then it's going to switch sides till again it reaches a maximum, and then decrease till it reaches 0, and then do the same thing. Simultaneously, the magnetic field will do exactly the same thing. So if I plot then the magnetic field versus time, so the magnitude of the magnetic field, here again, at time is equal to 0, I have 0. Then it's going to increase, 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 decrease, decrease, go to 0, increase in the opposite direction, maximum, decrease, decrease, 0. So plotting each one of these, I would then get a wave. So here I have a sinusoidal wave, which does something like this, etc. On this side, I also have my sinusoidal wave. And again, these two things are in phase with each other. So these two waves are in phase. They are perpendicular to each other. And what else? And here they satisfy all the usual wave stuff. So from here to here, this is then the period. Same thing from here. So the time takes to go from here to here is the period. And then if I plot them in space, then that would also be the wavelength in space. Okay. So what's happening is this wave is moving away. So it's moving outward. It's moving at a velocity of c, which is then equal, or the velocity equal to c. So each one of these is the direction at which the wave is moving. So notice that actually the direction of the wave itself is actually given by the right-hand rule. So here, if I was looking at this position here, I want to know the direction at which the wave is pointing. So I would point my fingers in the direction of the electric field, curl them towards the magnetic field, and then my thumb would point in the direction of the wave. So again, if I was thinking about this location here, so my electric field would point this way. So in this case, I point my fingers down in this direction, curl towards the magnetic field, which in this case is into the page. My thumb would then point in the direction of propagation. So the direction of propagation is then given by the electric field crossed by the magnetic field. So this is equal to the direction of propagation. So the direction at which that wave travels is given by the right-hand rule, where that right-hand rule is given by the cross product between then the electric field and the magnetic field. Okay. So this is the way antennas work. Now, it's actually a little more complicated. Let me show you here. So what ends up really happening is with an antenna, you actually get these closed circular loops. And what's actually really happening here is what? This is when the electric field is going in one direction. This portion here is when the electric field is going in the opposite direction. So what ends up happening is those two fields, which are going in opposite directions, end up superimposing on top of each other, which then create these circular waves. Okay. So basically, this wave will end up being circular and then travel outward away from our antenna. So this is only half the antenna. So the other portion of the antenna is going to be down here. Now, what's also going to happen is these circular portions of wave, as they go out further and further and further away from the antenna, they're going to start stretching further and further and further and further, until eventually what's going to happen is these circular pieces of wave, which are happening somewhere around here. So again, if I take this wave here and superimpose it on top of that one, so this one is what? Again, moving this way, superimposed on top of that. So it's going to give me this kind of circular wave. So my electric field is actually moving in more of a circular fashion. But as I start getting further and further out here, what will end up happening is that each one of these circles will then start to be stretched, and they're going to be stretched so that this wave will start moving basically parallel. Okay? So out here, we're going to get what are known as plane waves. So here, this is actually more of a circular wave, or let's call it a spherical wave. But then as it gets further and further out, that sphere starts getting stretched further and further and further, which ends up making these guys look like straight lines moving toward you. So in this part, the wave will then be moving simply in this direction with the velocity v equal to the speed of light. This is what we call the far field region. So the far field region is when these spherical waves have spread, or at least been stretched enough that they start to create plane waves, which means that these waves are actually just moving parallel to each other in the same particular direction. So this is what's called the far field region. Now, when we start talking about optics, this is the region that we really want to pay attention to, this far field region. So this is important for optics. So that'll be what we're going to do in next chapter. Okay. So good. So this is how we actually generate electromagnetic radiation. Okay. So we have to have some sort of time-dependent field. A lot of times that means we're going to have to accelerate some sort of charges. And one way we can do that is actually use a radio or an antenna to then create this source. So when we talk about electromagnetic radiation, most of us think about light, where we think about this small little portion here, which is that of the visible light. So let me make this bigger. So most of us usually think about this little tiny portion here. We talk about light. This is actually the visible light spectrum. But in reality, electromagnetic radiation goes from basically 0 frequency all the way up to infinite frequency. So this entire thing is the electromagnetic spectrum. So again, it goes anywhere from 0 frequency all the way up to infinite frequency. And remember that, going back to what we did with waves, remember the speed is equal to the wavelength times the frequency, which means as the frequency goes up, the wavelength goes down, or vice versa. So if it has a very large wavelength, that means it has a very small frequency. And if it has a very small wavelength, then it has a very large frequency. So typically, this is our electromagnetic spectrum. So for the very large wavelength, which have very small frequencies, these are what we call the radio waves. And remember, the energy is proportional to the frequency. So these are the very small energy region. So these are the radio waves. So typically, radio waves are going to have a wavelength of about the size of a football field to about the size of your car. It can go even smaller than that, so about the size of a human. Next up is microwaves. So microwaves are going to be as large as the size of a bee, pretty much down to about the size of a pinhead. So this is about the wavelength of a microwave. For infrared, so that's what's next. Infrared is about the size of a cell, down to about the size of a bacteria. After that is the visible spectrum. So visible spectrum will be about the size of something smaller than a cell, so about the size of like an atom. To about the size of a virus, somewhere around there. Ultraviolet, so ultraviolet, that's going to be about 10 to the minus 8 meters to about 10 to the minus 9 meters, so about the size of a nanometer. X-rays will be about a nanometer to about 10 to the minus 10, 10 to the minus 11. And then finally, gamma rays. So gamma rays will be about the size of a nucleus, so about 10 to the minus 12 wavelength. So these things have the greatest amount of energy, so these are the most energetically of the electromagnetic radiation. So, quick question. Anybody know why an AM radio has no antenna? So if you think about your car, right? Your car usually has an antenna about that big, and that's for FM radio. But if you look at an older car, which only has AM radio, there is no antenna. So anybody know why there is no antenna for an AM radio?
Is it because the wavelengths are longer?
Correct. So it's exactly right. The wavelengths are longer, and the wavelength is about the size of your car. So actually, your car is the antenna for AM radio. So AM radio is actually you didn't need an antenna because your car was the antenna. So it actually picked up the entire wavelength based on the size of your car. Another interesting fact is that AM radio actually travels through the ground. So when they send out AM frequencies, it actually travels through the ground. So your car actually picks it up from the ground. So it's not like FM where it actually puts it out into air, where it can actually be dispersed a lot easier, but it actually goes through the ground. So yeah, so this is the electromagnetic radiation, the electromagnetic spectrum. Typically, these things are actually temperature dependent as well. So for large wavelengths, for low energies, these things have a particular color. So this is why we know when we look at the sun, for example, the sun is yellow, so we know that temperature is about 6,000 Kelvin. And it's based off of the frequency. So it has the most prominent frequency is then based off of a particular color at which you actually see. So I guess that's about as much as I'll say about that. But again, so most people, when they think about light, they think about the visible light. But again, everything here is part of the electromagnetic spectrum. So it actually goes from 0 wavelength all the way out to infinite wavelength, or from very large frequency, to very small frequency. I'll say that backwards. So good. So what do we know about light? So we know light is an electromagnetic wave, and since it's a wave, we then know that what? This thing carries energy. So we know that E and M waves carry energy. So we basically want to know how much energy do they carry. So how much energy do they carry? So to do this, let's look at the total energy density. So remember that energy density, we had the electric energy density, which was 1/2 epsilon naught times the electric field squared. And we also have that the magnetic energy density was 1/2 the magnetic field squared divided by mu naught. So the total energy density then is going to be the electric energy density plus the magnetic energy density. So it's going to be the same thing then as 1/2 times epsilon naught times the electric field squared plus the magnetic field squared divided by mu naught. Now, one thing we learned from velocity selectors and from the Hall effect is that the velocity of the wave is actually proportional to the electric field divided by the magnetic field. So as long as this thing is traveling in vacuum, then that means that the speed of light is then equal to the ratio of the electric field to the magnetic field. So I'm going to go ahead and use this here. So I'm going to rewrite this then as 1/2 epsilon naught times the electric field times, so in this case, I'm going to rewrite one of these electric fields then as the speed of light times the magnetic field. So that's one of my electric fields. So this tells me that what? The electric field then is equal to C times B. There we go. Plus the magnetic field, and I'm going to rewrite one of these magnetic fields. So this one also tells me that the magnetic field then is equal to what? The electric field divided by the speed of light. So this is then going to be equal to electric field divided by mu naught times the speed of light. So if I keep going with this, basically what this will turn into then is that what? This term here times C is actually the same thing as this term. So this is actually the same thing as 1/2 times twice of the electric field times the magnetic field divided by the speed of light times mu naught. So this thing actually ends up becoming the electric field times the magnetic field divided by C times mu naught, okay? Which means that the total energy, let's write that as potential energy, then is equal to the total energy density times the volume. Okay? Good. So the volume is, so let's say here's a beam of light moving in this direction. So this is going to have some cross-sectional area A, and it's going to move over some length L here, where L then is going to be equal to the velocity times the change in time. So this is then going to be equal to the electric field times the magnetic field divided by C times mu naught times then the cross-sectional area times C times the change in time. So the C's here are going to cancel. So this is going to become the electric field times the magnetic field times cross-sectional area divided by mu naught times delta T. So what this tells me then is that the total energy at which the wave is carrying is actually equal to the electric field times the magnetic field magnitudes divided by mu naught times the area times the change in time. Now typically, we're going to be interested in is something similar to that, which is going to be equal to the energy per area per change in time. So this is going to be equal to E times B divided by mu naught. Okay. So this is the energy per time per cross-sectional area is then equal to E times B divided by mu naught. This is what we call S, at least the magnitude of S, which is actually an intensity. So what this says is that the intensity of the light, so what this means is if I have light traveling in this direction at the speed of light c, this is then the area per I'm sorry, this is the energy per unit time per unit area, which is then delivered to this cross-sectional area. So this is then the intensity. So the intensity then is, again, 1 over the area times the change in energy per change in time. So this is power per area. So this is a power per area, which again is an intensity. So this says then that the intensity of the light is then equal to the electric field times the magnetic field divided by mu naught, which is what we call S, which is then equal to an intensity. Now also remember earlier we said that the direction of the electric field, or the direction at which the wave propagates, is the cross product between E and B, which means that S is actually a vector, which is then given by E cross B divided by mu naught. This is what's known as the pointing vector. So what is the pointing vector? So the pointing vector then is, first of all, it points in the direction of wave propagation. So the pointing vector, first off, tells me the direction at which the wave is traveling. Second of all, the magnitude tells me the intensity of the light. So the light then is determined, or at least its intensity is determined by this pointing vector, which again depends on the electric field and then of the magnetic field. Now, what we also talked about is that the electric field is oscillating. So this is actually oscillating as a wave. The magnetic field is also oscillating as a wave. So if I'm talking about a high energy wave, this thing is going to be oscillating very, very rapidly, which means on average, we're typically not going to measure the electric field and we're not going to measure the magnetic field. What we're really going to measure is actually the RMS values of the electric field and the magnetic field. So typically for us, what we're going to do is we're going to write the magnitude of then the pointing vector, which again is the intensity, is going to be the RMS value of the electric field times the RMS value of the magnetic field, all divided by mu naught. So this is what we're going to write as then the intensity. So remember, intensity then is the amount of energy per unit time delivered to a cross-sectional area. So this is what we call the intensity. Okay. So again, we're measuring here the RMS value because this thing is oscillating so rapidly, we can't really measure what its instantaneous value is. We can just measure kind of its average value. But remember that since this thing is oscillating like this, the average value is actually equal to 0. So the average value of the electric field is actually going to be equal to 0, which is why we're measuring the RMS value. Remember, the RMS value is equal to what? The square root. So the amplitude divided by square root of 2. So remember, RMS value is actually equal to the square root of the average squared divided by 2. So this is what we call the RMS value, where this is then the amplitude of the electric field. Okay. Everyone's okay? So you got a little lost in that math there. Don't worry too much about it. All you really want to know is this part. This is what's important. Okay. So good. So let's use this and let's do an example. So my first example says, where am I? There it is. That we have radiation from the sun reaches the earth above the atmosphere at a rate of 1,350 watts per meter squared. So that's the intensity. So it wants us to assume that this is monochromatic light, so that it has one single frequency. And it wants us to calculate the maximum electric and magnetic field. So what is the amplitude of the electric field and that of the magnetic field? So good, let's draw a pretty picture. So here is the Earth. Here's the atmosphere. Here is the sun. And then light is coming in and impinging then onto the atmosphere. And what we're told is that the intensity is equal to 1,350 watts per meter squared. So from here, we want to know then is what is the amplitude then of the electric field and what is the amplitude of the magnetic field. So we want to know what are each one of these guys equal to. Okay. So good. So what do we know? So first off, we know that what? The intensity then is equal to the magnitude then of the Poynting vector, which is then going to be equal to the RMS value of the electric field times the RMS value of the magnetic field divided by mu naught. What else do we know? So we also know that, again, the electric field, RMS, is equal to the amplitude of the electric field divided by the square root of 2, and the magnetic RMS value then is equal to the amplitude of the magnetic field divided by the square root of 2. So this is the same thing then as the amplitude of the electric field times the amplitude of the magnetic field divided by 2, or square root of 2 squared, times mu naught. Now we also know that since C is equal to E divided by B, that means this is also equal to the amplitude of the electric field divided by the amplitude of the magnetic field. So here, even though we have two unknowns, E0 and B0, we can then use this to rewrite it in terms of one unknown. So for example, this tells us then that B0 then is equal to what? E0 divided by C. So we can rewrite this then as what? E0 squared divided by 2 times C times mu naught. So from here, we can solve for the electric field. So the electric field amplitude then is going to be what? The square root of 2 times C times mu naught times the intensity. So it's going to be the same thing as the square root of 2 times 3 times 10 to the 8th times mu naught, where mu naught was 4 pi times 10 to the minus 7 times the intensity, which was 1350. Plug in my numbers. What I find in this case then is this works out to be about 1.01 times 10 to the 3rd volts per meter. So this is then the amplitude of the electric field. From over here, we can then find the magnitude of, or the amplitude of the magnetic field by just taking that E0 and divide by C. So this tells me that the amplitude of the magnetic field then is going to be 1.01 times 10 to the 3rd divided by 3 times 10 to the 8th. So plugging my numbers, this works out to be about 3.37 times 10 to the minus 6 Teslas. So this is the amplitude then of the magnetic field. Okay, not too bad, right? Now we also know that what? Magnetic or any waves carry momentum. So this means that electromagnetic waves carry momentum. Or more appropriately, remember from 175 that a change in momentum with respect to time is equal to a force, which means that we can actually get a force out of electromagnetic waves. And this is what we call radiative force. But also remember from 175 that force per unit area is actually equal to a pressure. So we can actually then get what's known as a radiation pressure. So we can actually create a pressure onto objects by just simply shining light onto it. So, question then is how much pressure can we get, how much force can we actually get by having a change in momentum? So let's look at two different cases. So first case is, let's have our light then hit some object. So here's our object. So here's my light coming in, so let me draw my light. So it's gonna hit this surface, okay? So case number one is that the light is absorbed. So we're going to allow our light to become absorbed. Case number two is that the light is actually going to be reflected. Which means that in this case, then our light is going to be reflected back in this direction. So it's going to be our light's reflected. So in the first case, it's going to come in, hits, become absorbed. So it's going to be completely absorbed by the material. In the second case, it's going to hit and then be reflected and bounce back off in the opposite direction. So let's look at case 1 first. So good. So here we know that the change in momentum then is going to be equal to what? The final momentum, or the final momentum is going to be equal to 0, minus then the initial momentum, which means that the change in momentum then is simply going to be equal to the initial momentum with a negative sign. But here, let's look at the magnitude of it. So it's just going to be the change in momentum. Case number 2, what's going to be different then is that what? Initially, it's going to be moving in, so the final momentum, but remember that momentum is a vector, so we have to define a coordinate system. So let's say take positive x to be in this direction. So for case number 2, the change in momentum then will then be equal to minus the final momentum, minus then the initial momentum. But if this is a completely elastic collision, so let's pretend this is completely elastic, this means that what? The final momentum is actually equal to the initial momentum, because we're assuming that this thing has basically an infinite mass. So mass here goes off to infinity. So this means then that the change of momentum then is going to be equal to twice of the initial momentum. So what's different between case 1 and case 2 is case 1, the change of momentum is just equal to that of the initial momentum. Case 2, it's equal to twice that of the initial momentum. So it turns out that regardless of which case we're looking at, the change in momentum is then equal to the change in potential energy divided by the speed of light. Good. So this means then that's what? The force, or the radiative force, then is going to be equal to the change in momentum divided by the change in time. So it's going to be then equal to 1 over the speed of light times then the change in energy divided by the change in time. So this is then the radiative force. We'll talk more about this in a second. And then from here, we can get the pressure is then equal to, I'm going to write this as pressure rad, is then equal to the force per unit area. So this is then going to be equal to 1 over the speed of light times 1 over the area times the change in potential energy divided by the change in time. But we also know that this quantity here is simply the magnitude of the Poynting vector. So this means then that the radiative pressure is then equal to what? The magnitude of the Poynting vector divided by the speed of light, which is actually equal to the intensity divided by the speed of light. So the radiative pressure is then equal to the intensity divided by the speed of light, which means that the radiative force is then going to be equal to what? The cross-sectional area times the pressure, which is then going to be equal to the area times the intensity divided by the speed of light. So this is then the radiative force. So what does this mean? So this means that if I went outside and I put my hand in a nice bright and sunny day like it is right now, even though my phone originally told me it was supposed to rain all day, but that's fine. That means when I put my hand outside, that light is going to come down and hit my hand and then apply a force to my hand. Meaning that my hand is going to be pushed down due to this force by the light actually striking it. So what I want to know in this case then is radiation from the sun that reaches the surface of the earth transports energy at a rate of about 1,000 watts per meter squared. So estimate the pressure and the force exerted by the sun on my hand. So let's do that. Okay, let's say that I'm standing outside. So here I am outside with about 1,000 pounds of sunscreen on because I am very white. There we go. So there's my hand, overly sized, overly huge hand. Okay. And then I have light, which is coming down. So here's the light coming in from the sun. And what I'm told is that the intensity from the sun is 1,000 watts per meter squared at this height. Okay. So that then is going to result in a downward force, which is then going to be the radiative force, and also a pressure as well. So what I want to guesstimate then is what is the radiative pressure, and then what is the radiative force. So for the radiative pressure, what I know is that this is going to be the intensity divided by the speed of light. So in this case, this is simply going to be 1,000 watts per meter squared divided by the speed of light, which is then 3 times 10 to the 8th meters per second. Which means if I plug in my numbers, what I find in this case then is this works out to be about, 3 times 10 to the -6 newtons per meter squared. So the amount of pressure that I feel on my hand from the sun is going to be about 3 times 10 to the -6 meters per second, or sorry, newtons per meter squared. So now I want to know what is then the radiative force. So how much force does my hand feel? Well, to do that, we have to assume some dimensions for my hand. So let's assume my hand then is about 20 centimeters in this direction. And let's say it's about 10 centimeters wide. Okay. So if I'm holding my hand like this, I'm saying it's about 20 centimeters from here to the tip of my finger and about 10 centimeters wide, so that way I can get an area. Right? So in this case, my area then is going to be, what, 0.2 times 0.1 meters squared. Okay, so the radiative force then is going to be simply the area times the radiative pressure. So it's going to be 0.2 times 0.1 times then 3 times 10 to the -6. So it's going to be the same thing then as what? 6 times 10 to the -8th newtons. So the radiative force then that my hand is feeling from the light hitting my hand, pushing it downward, is only about 6 times 10 to the -8 newtons. Is that a big or a small number? Comparatively.
It's a very small number.
A very small number, right? Because my hand itself has about 2 newtons at least 2 newtons worth of force pulling it downward purely from its weight, right? So that means that what? This little tiny amount of force, as far as my hand is concerned, is basically nothing. Right? So radiative force and radiative pressure for large objects such as like my hand or the earth itself is basically 0. It doesn't actually do anything. But radiative force is actually a big deal when it comes to other things. For example, simple charged particles which are flying around in the atmosphere are going to feel a huge amount of force because of that light pushing on it. Other things is, in the early universe, especially when I had light from stars, which is then pushing onto gas clouds, those gas clouds would then be pushed together because of that light, which would then cause overdensities, which would eventually create things like planets, right? Solar systems, things like that. Other things that it's actually huge on are atoms, DNA. So this is actually what's called optical tweezing. So the reason that we know the length of DNA is actually because of lasers. So you can actually shine lasers from different directions onto something which has a very small mass, and it actually acts like a tweezer. So this is what's called optical tweezing. So by shining it onto something like DNA, you can actually stretch out and move the DNA and move it in any direction that you want to by simply using the lasers to then direct the direction in which you want it to go. So by shining light onto it, you can actually get it to move in different directions. Also, if anybody's had LASIK surgery before, they actually use lasers. So you're actually using the laser to cut through from this radiative force and this radiative pressure. In those cases, you have a much higher intensity. So instead of something like 1,000, you have a much, much greater intensity from the light beam. So again, on something that's large scale and something that actually weighs a lot, you don't get a lot of force or a lot of pressure from this radiation of the lights, but something that's small scale, so things like atoms and things, you can actually move them around. You can manipulate them by simply shining lasers onto them. You can also float things using lasers by simply shining light at them. You can do a lot of different things with this optical tweezing. So this is radiative pressure. Everyone okay? Not too bad, right? So that brings us to our group exercises for today. Exciting. So the first two, I'll bring these up. So this says we have high energy pulse lasers emit 1 nanosecond long pulses of average power of 1.8 times 10 to the 11th watts. The beam itself has a radius of 2.2 millimeters and wants to determine the energy delivered by the pulse, so how much energy is delivered in that 1 nanosecond pulse, and then the RMS value of the electric field. So this is going to use the intensity. The second one says, this is another good example of using radiative pressure, that in 2004, Japanese scientists successfully tested 2 solar sails. So one had a somewhat complicated shape that is modeled as a disk, which is 9 meters in diameter, 7.5 micrometers thick. The intensity of the sun at the location was about 1,400 watts per meter squared. So it wants to know, what force did the sun's light exert on the sail, assuming that it is struck perpendicular to the sail. So basically the sail's here, the light is coming in here, so it's hitting 90 degrees to that. And we want to know, do we want to use a reflecting or an absorbing? Oh no, and that sail was perfectly reflecting, okay. Good, so it wants to know what was the force. The second part then says, if the sail was made out of magnesium, so it has a density of 1.7 grams per centimeter cubed, which is 1,700 kilograms per meter cubed, what acceleration would the sun's radiation give the sail? Based off that acceleration for part C, does that acceleration seem large enough to be feasible for large space travel distances? And I'll give you an answer for that. The answer is no. The acceleration is ridiculously small, so no. And then it wants to know, in what ways could the sail be modified to increase the acceleration? So basically, what I'm telling you here is the density, which is then determining the mass. So basically, to get it to accelerate more, do you want it to have more mass or less mass? So with a fixed amount of force, if I want to increase the acceleration, do I want to increase or decrease the mass?
You want to decrease it.
Exactly, you want to decrease, because remember, Newton's second law says the force is equal to mass times the acceleration. So basically, what this thing then is asking you is, how can you modify the sail here to decrease the mass of the sail? So if I want to increase the acceleration, I have to then decrease the mass. So in this case, I want to decrease its mass as much as possible. So how could I do that? And that brings us to the third one. So let's talk about the third one. So the third one says, someone plans to float a small, totally absorbing sphere 0.5 meters above an isotropic point source, so that the upward radiative force from the light matches the downward gravitational force of the sphere. The sphere's density is 19 grams per centimeter cubed, so that is 19,000 kilograms per meter cubed, and has a radius of 2 millimeters. So it wants to know what power of the source would be required of the light source, and even if such a source were made, would it be possible to support the sphere to be stable? The answer to that is, well, no. It might float there, but as soon as it rocks in one direction or another, it's just going to fall down. Okay? So let's kind of draw what's happening with the third one. So for the third one, what's happening is I have an isotropic source. So isotropic source is sending light evenly all directions. So this is creating a sphere. And then up here, I want to put a small little tiny sphere, which has a radius of r, right, which was equal to what, 2 millimeters. And this is a distance, let's call that d, where d is then 0.5 meters above here. So since this thing has a mass, what's going to happen is I'm going to have a gravitational force pulling downwards. So there's going to be mg here. We now know the radiative force is going to push off in this direction, so we're going to have radiative force. What we want is for this thing to float, which means that the sum of the forces in our y direction here are simply equal to 0. So we're going to say the sum of the forces in the y direction are equal to 0. So I'm going to get the radiative force minus the weight is equal to 0, which means the radiative force is then equal to the weight. Right? Good. So from here, we then have to what? Again, we know radiative force is then going to be equal to, oh, we need to go back to that for a second. I'm going to talk about something. So this is going to be equal to the cross-sectional area times A times I divided by C. So what is A here? So let me go back to what A is in a second. That's going to be important. Good. And remember that intensity for an isotropic source is equal to the power divided by the cross-sectional area. So in this case, This area here is the what? Surface area. Where this area here is then the cross-sectional area of this guy. So this is going to be the cross-sectional area. So this area here is different than this area here. So remember, for an isotropic source, this is going to be equal to the power divided by 4 times pi times the distance squared. Where this area here, which is the cross-sectional area, is then equal to, so what is this? It's going to be pi times the radius squared. So those two areas are going to be different. So this area here is based off of this sphere, and then this area here is based off the cross-sectional area of this sphere. Okay. So let's talk about A here. So let me go back. So I made a point to start talking about this, and then I forgot to finish my thought. So let's go back to here. So the difference between case 1 and case 2 here, again, was this factor of 2. So here, the change of momentum when was equal to simply the initial momentum. Here, the change of momentum then was equal to twice of the initial momentum, which means that actually when I went through here, when I wrote all this down, the difference is in case 1, I end up with this, but in case 2, so let's go back to case 2. I forgot to write down case 2. In case 2, you actually end up with the radiative pressure then was equal to twice the intensity divided by C. Okay. So in general, we're going to write that the radiative pressure then is going to be equal to A times I times C, where A is some number between 1 and 2, where 1 corresponds to when it is completely absorbed, and 2 corresponds to when it is reflected. Sorry, I forgot to mention this earlier. Reflected. Okay. So basically, when you do a problem which involves radiative force and radiative pressure, you have to know, is it being completely absorbed or is it completely reflected? So basically what will happen is, if it's being completely absorbed, you get half the amount of radiative force and radiative pressure that you would get if it was being reflected. And again, the reason for that is traced back to here. So again, in case 2, you get this extra factor of 2 because it hits and then gets reflected off, which means the change of momentum is twice the size. Okay? So when it is reflected, you get twice the amount of radiative pressure and radiative force that you would get from being absorbed. Okay? Now here, in this problem, for number 3, you're told that this guy is what? Totally absorbing. Okay? So in this case, you're going to use that little a here is simply equal to 1. But if it was reflecting, in that case, you would use a would then be equal to 2. Okay? So that's basically the only difference. So that brings us back to the sail problem. Well, the sail problem is asking, do we want it to be reflecting or do we want it to be absorbing? Well, in this case, we want it to be reflecting because that's going to give us the greatest amount of force. Right? So for question 2 here, we want to use that a is equal to 2. So little a is equal to 2 in this case. That's okay. Sorry, I forgot to mention that. All right, so don't have a huge amount of time, so about 6 minutes, so at least you can start talking about these. So tomorrow we'll start off, give you a little more time to kind of work on these a little bit more, and then we'll start moving. And by the way, that's the end of chapter 22. So we're already done with chapter 22. So the rest of the time we're going to work on chapter 23. So how many people we got today? We got 1, 2, 3, 4, 5, 6, 7. We'll do 2 rooms. Sounds good. All right. we doing, ladies?
I think we're all just opening like the document and taking down the given information still.
Sound good.
Oh man, I don't know. I'm moving slow today. I'm
You're not the only one.
tired.
Yeah, my wife decided that I was bringing our son to his second day of kindergarten today, so it's been
Oh, yeah.
fast ever since I woke up this morning. So got up at 4:30 and I haven't stopped moving since then. So.
So for the first one, when we're calculating the energy delivered, is that going to be, are we going to use the power?
Yeah, so remember,
calculate
power
that?
is change in energy divided by change in time. Yeah.
Time.
So in this
Right.
case, you know the power, you know the time. The time is just 1 nanosecond, so that gives you the energy.
Okay. Making sure that I'm not overcomplicating it or oversimplifying it.
Like we like to do. That's right. Good. Yeah. So here I gave you the radius of the beam, but you don't ever need that, so that's fine. Yeah. And then part B, you know actually no, I'm sorry. You do need the radius. Because for part B, you know the power. So then to get the intensity, you need to divide that by the area. So that's just pi r squared. And then the intensity is equal to the RMS value of the magnetic field times electric field divided by mu naught. So, yeah. So like that example that we did. So, yeah.
Yeah, for A, I got 180. And then for B, I got like 2.11 times 10 to the 9.
Sounds about right.
Okay.
Yeah, I don't remember quite what they are, but yeah. Good. Yeah, 180 is correct. Yeah, good. All right. You want to check on the other guys when you're back?
In order to find the intensity, you would take your watts and then you would convert the beam into meters squared. And that will give you your intensity. You would plug that into your E naught equation, and then you would take your E naught equation and then divide that by the square root of 2 to get your ERMS.
That's right. Yeah. So here for the area, you only need the cross-sectional area, not the surface area. So you're only going to use pi r squared instead of 4 pi r squared. But yes.
Oh, okay.
Yeah. Difference is here, it's not an isotropic source. It's just a beam. So yeah.
Okay. Okay. Thank you for that.
No problem. Are you sad the Maple Leafs lost?
Well, yeah, because after Game 4, they kind of deserved it. Game 4, I mean, I was getting ready to throw stuff. I was kind of upset. I was upset with Marner's effort, and then they came back, and then last night I had and it didn't work. So
Yeah.
but yes, I am.
4, they were what, up by 3? Is that right? Is that what
Game 3, yeah, they were up by 3, blew that lead, as you know we're used to. And then being on the other side of that was pretty nice on Friday, and then they just didn't score. Corpusella, he stole that game, so congrats to them. So
that's all right. My team was the worst team in the league this year, so that's fine.
Oh, you're a Red Wings fan?
Yeah, I've been one since the 90s, so yeah. Nothing
I
to
apologize.
brag about these years. So.
Oh, I apologize, sir.
Everybody goes through these. It's fine. Yeah, they were fun to watch when they had the Russian 5 and everybody back in the day, but no.
Yeah, it was fun watching Datsuk flip people in the shootouts, but nowadays I think you can take your local rec league team and they would try to put up a fight against. Yeah.
Yeah, probably hold their own against them. That's right.
Yeah, probably.
Oh well, what are you gonna do? So we are officially out of time. So you guys can keep working if you want to. Otherwise, like I said, I'll give you some more time tomorrow morning. Kind of start working on them, but But yeah. Otherwise, have a good day. Remember, no lab today, and I'll see everybody tomorrow.
See ya.
Bye. All right, so we are officially out of time. So, but feel free to keep working, and like I said, I'll give you more time tomorrow. Kind of work on these things and go from there. But yeah, everyone's doing okay. You finish off with number 1.
Yeah.
Yes. Okay. Everybody's more quiet today.
All right. See you tomorrow.
What's up?
Oh, I said see you tomorrow.
All right. Sounds good.